We're back. Sorry about that. The last video ended a little bit abruptly. I guess I thought I had more time than I actually did in that video. So as we were saying before, we're putting together everything that we've been talking about here in terms of the types of messages that neurons communicate with one another, those messages being either excitatory messages or inhibitory messages, and the fact that whether or not a particular neuron generates an action potential, whether or not it fires, depends on the total amount of excitatory and inhibitory inputs that are converging onto that neuron, right? So the total number of excitatory and inhibitory inputs will determine whether this is a neuron, whether this neuron fires. Okay, so imagine here's a particular picture of a neuron here, and we'll sort of look at all different sort of examples of what sorts of things affect the firing rate. So imagine this, all of these A, B, C, D, E are all the same neuron, right? And so it's got some degree of convergence in the sense that at least two neurons are converging onto this particular neuron that we are recording from. You know, for scientists, that we have a recording electrode stuck into the axon of this cell, and that allows us to record the number of action potentials that this cell is generating in response to the input that it's getting from these two cells over here. So there's a neuron here, and there's a neuron here. And so, importantly, so we know that whether this neuron fires, well, the activity of this neuron, the firing rate, is affected by the amount of convergence, number of cells that are contributing inputs to this neuron. And more than that, it depends on the total combined amount of excitatory input and inhibitory input. These two things add together. So imagine this cell is only, this cell that we're recording from is only at this moment in time, at one particular moment in time, is only receiving excitatory input. Okay, so what is the activity of that cell going to look like? Here we're looking at the plot over here. Each one of these little hash marks here indicates that an action potential has happened, and so we're looking at the number of action potentials that occur over the course of time. So this is time, and this line here indicates the moment at which the stimulus turns on, and this moment here indicates the moment at which the stimulus turns off. So a couple of things to notice. First of all, you'll notice that a couple of action potentials occur even before the stimulus is applied to this cell. And the reason for that is, as we said last time, or last class, that it's not as though neurons completely shut off when they're not being stimulated by some stimulus out in the environment or by a neighboring neuron. Neurons have sort of a baseline level of responding where they'll generate a couple action potentials here and there. But what happens when a stimulus is applied? That's what, we can look at how this cell, its behavior, if you want to call it that, its activity changes following the time at which the stimulus is applied. If it's only receiving excitatory input, then the rate of firing will increase rapidly, right, until that stimulation has stopped. So until it has stopped receiving this excitatory input, right? So a cell that receives only excitatory input will generate more, it will generate action potentials more rapidly. But what happens if we start adding in some inhibitory inputs? So it's still receiving an excitatory input, but now it's also starting to receive some inhibitory inputs as well. So what does that do to the rate of firing of the cell? Well, compare this event to this event. We see that applying a stimulus, right? So these two events, a lot of excitatory input and a little bit of inhibitory input, still causes the cell to increase its firing rate above baseline, right? Above this is baseline, but not nearly as rapidly as as what we saw up here, right? So adding some of that inhibitory input subtracted from sort of the excitatory message here. Okay, so the firing rate of a cell is always the sum total, or is a result of the sum total of the excitatory inputs to the cell as well as the inhibitory inputs to a cell. So what happens if the excitatory messages and the inhibitory messages are exactly the same? So this cell receives exactly the same amount of excitatory inputs and inhibitory inputs. Basically what you see is that the cell's activity doesn't change from baseline, right? It generates a couple action potentials here and there, even when the stimulus is not being applied. And it basically just continues at that same rate of responding, even when it's receiving these messages from this presynaptic cell. So, and why is that? Because it's basically the same thing as just not getting any sort of input at all. Why? Because the excitatory input is being completely offset by the inhibitory input. Okay, and so to just sort of skip down to this last one here, this is sort of the flip side of the first example that we showed up here. Imagine that this cell now is only receiving inhibitory inputs, and it's not receiving any excitatory inputs. What is that going to do to the activity of this cell? It's actually going to turn it off, right? So here's the baseline activity of the cell. It generates a couple action potentials here and there, but once this inhibitory signal starts up and it's only receiving inhibitory messages and there's no excitatory messages to offset that, then this cell essentially just kind of completely shuts off. Okay. So the lesson or the idea to keep in mind here is that the activity of a cell is always a result of the sum total of the total amount of excitatory input to that cell and also the total amount of inhibitory input to that cell. Those two things always add up together. Okay, so we've said a little bit about some of the differences between the rods and cones. We mentioned in the last video, rods are more sensitive to light, and we saw that also in our discussion, as I said before, of dark adaptation. Rods are more sensitive to light. What does that mean? It means that it takes less light for rods to respond. Rods can respond to a lower level of light, a less intense light than cones can, right? It takes more light. It takes light of a higher intensity, a brighter light, to stimulate a cone than to stimulate a rod. So you can think of it as, if you like to think of it in terms of threshold, right? Rods have a lower threshold for responding, right? Because they will be stimulated by lower levels of light of less intensity. And we'll see on the next slide that the reason for this is because of what we've already said before, that rods have a greater convergence. They converge to a much larger degree on ganglion cells than cones do. Okay, so this property, this fact that rods have greater convergence than cones, is actually what gives them their greater sensitivity to light. But there's a trade-off. So although greater convergence, the fact that rods have a greater degree of convergence onto cones, gives them better sensitivity to light. They're able to respond to less intense lights than cones are. There's a trade-off in the sense that rods can't distinguish detail. So the greater convergence of rods really produces two things. It gives rods better sensitivity to light, but it makes it more difficult for them to make out fine detail. And let's take a look at why that is. Here's a picture showing a simple neural circuit, this is called. And a neural circuit is simply sort of a bunch of neurons kind of wired together. So on the left here are 5 rods, and on the right are 5 cones, and not just 5 cones, 5 foveal cones. Point out why that is in a second. So here's a rod, here's a rod, here's a rod, here's a rod, here's a rod. And all of these rods are converging onto a single ganglion cell. So this red thing here is a ganglion cell. And as it says over here, in order for signals to make it to the brain, this ganglion cell needs to fire. So in order for you to see, this ganglion cell needs to fire, right? Because if this ganglion cell doesn't fire, then the signals aren't going to reach the brain, and so there's going to be nothing telling the brain that there's something out in the physical environment, right? So these are sort of spots of light that might stimulate each of these rods, right? Rods detect light. So these are lights out in the physical environment that will cause stimulation of these cones, or these rods. And in order for you to perceive these lights, not only do these rods have to be stimulated, but they have to stimulate this ganglion cell, and this ganglion cell needs to transmit its messages onward up to the brain. Okay? And I think we're going to run out of time on this video, so I'm going to stop this right here, and we'll pick up in the next video with this slide in terms of talking about how the different amount of convergence between these two rods and cones gives these different sort of properties to rods and cones, in the sense of rods being more sensitive to light but having lower visual acuity, which means they can't see detail as well as the cones. And the flip side is that the cones are less sensitive to light, so it takes light of a higher intensity for them to respond. But they have greater visual acuity. We'll take a look at why that is in the next slide. But one thing to just sort of point out here, so you'll notice that there's lots of convergence here in this neural circuit here. So all of these rods are converging onto just a single ganglion cell, right? You can notice that these are foveal cones, right? Why? Because there's no convergence, because each cone gets its own ganglion cell. So this ganglion cell receives inputs only from this cone. It's not receiving any input from this cone, or from this cone, or from this cone, or from this cone. Okay, so there's no convergence over here. So this would be what the situation looks like for cones in the fovea, no convergence. Whereas this is the situation for rods. Lots of convergence. All of these rods converging onto this single ganglion cell. Okay, we're going to stop it there, and I'll be back in the next video to talk a little bit more about this.